In this video for section 13.7, we'll be doing some examples of finding equations of tangent planes and equations for normal lines at given points. Try this example on your own, pause the video, and come back and check your work. In this case, we have the surface x squared plus y squared plus z squared equals 11. That, if you recognize it, is an equation for a sphere centered at the origin, and the radius of that sphere is the square root of 11. So that looks, we're looking at a sphere in space, looking at a point on the sphere. We want to find the equation of the plane that's tangent to that, as well as the equations for the normal line. We want to begin by writing a capital F of x, y, z. That is x squared plus y squared plus z squared minus 11. Subtract 11 from both sides so that you get this equals 0. So here we have a function of those three variables. The gradient of this function is going to be used for the components of the normal vector to the plane as well as the parallel vector for the line. So the gradient of this function of x, y, and z is a vector, and the components are the partial derivatives with respect to x, y, and z. The derivative with respect to x is 2x. The derivative with respect to y is 2y. And the derivative with respect to z is 2z. Okay, so those are your components of your gradient vector. We're going to evaluate this gradient vector at our given point. At the point 3, 1, 1, we can substitute 3 for x, and we get 2 times 3, 6i, plus 2 times 1 is 2j, plus 2 times z, or 2 times 1 is 2k. So that is a vector. I can switch to the angle bracket notation, 6, 2, 2. The components are 6, 2, 2. This is going to be your normal vector to the plane. So the components are going to be a, b, and c. This is going to be your normal vector, and this is going to be your point. And you're going to use those to find the equation of the tangent plane. Okay, so the tangent plane, using the a, b, and c as your coefficients and your point 3, 1, 1, again, the equation of a plane is in the form of a times x minus x sub 0 plus b times y minus y sub 0 plus c times z minus z sub 0 equals 0. So this is going to be your x sub 0, y sub 0, and z sub 0. That's your point given. Now we can use that to find the equation of the plane. It's going to be 6 times the quantity x minus 3 plus 2 times the quantity y minus 1 plus 2 times the quantity z minus 1. Again, I'm using for the A, 6, B is 2, C is 2, and then I use the point x sub 0 is 3, y sub 0 is 1, and z sub 0 is 1. Now you can distribute this and combine like terms, divide any common factors to simplify this equation. If we distribute, we get 6x minus 18 plus 2y minus 2 plus 2z minus 2. Sorry, that should all be equal to 0. And when we rearrange the terms here, we get 6x plus 2y plus 2z. You have negative 18 minus 2 is negative 20, minus 2 is minus 22 equals 0. And then we could divide everything here by 2 to get the equation of the plane. Is divide everything by 2 and we get 3x plus y plus z minus 11 is equal to 0. That's your equation of the tangent plane. simplified. Now to find the equation of the parametric equations for the normal line, you're going to be using a point. You need a point, same point here, and a parallel vector. We're going to be using the normal vector. And the equations for a normal line are in the form of x equals x sub 0 plus at, y equals y sub 0 plus bt, and z equals z sub 0 plus ct. Now we can plug in what we know, so we can find x is equal to our starting x is 3 plus our 6t, y is equal to 1 plus 2t, and z is equal to 1 plus 2t. Again, I use the points and the normal vector components to come up with the equations, the parametric equations for the line, the normal line. Now this is not unique. There are an infinite number of ways of doing this. I'm presenting you with one approach. Alright, now let's try this one. Okay, for the given surface, find the equation of the tangent plane and parametric equations for the normal line. Now here we have a function of x, y, and z, so we can say that that is our capital f of x, y, z. It's already equal to 0. Okay, we can find the gradient of that capital F of x, y, z. Those are going to be the components of your normal vector. That's a vector that is normal to the surface. When you take the gradient, again, you're taking the partial derivative with respect to x. You can take the partial derivative with respect to y, and the partial derivative with respect to z. Now the partial derivative with respect to x, you're treating x as a variable and everything else as a constant, so that partial derivative is going to be z e to the x squared minus y squared times the derivative of the exponent with respect to x is 2x. That's your I. Plus the partial derivative of this capital F of x, y, z function with respect to y. Treat y as a variable and everything else as a constant to get z e to the x squared minus y squared times the derivative of the exponent, where you treat y as a variable, x as a constant. That derivative is negative 2y j, plus the partial derivative of all this with respect to z. Treat z as a variable and x and y as constants, and that is e to the x squared minus y squared, that times k. Now let's evaluate the gradient at our given point. This point given is x sub 0, y sub 0, and z sub 0. The gradient is going to help us find our a, b, and c. When we evaluate the gradient at the point 2, 2, 3, plugging in 2 for x, 2 for y, and 3 for z, and then simplifying, we get this will all simplify to 12i. This will all simplify to minus 12j, and this will all simplify to 1k. So this is going to be your ABC, your 12, negative 12, and 1. That's going to be the components of your normal vector. That's your A, B, and C. Alright, now let's find the equation for the tangent plane. So our tangent plane, we're going to use the A, B, and C as coefficients and your x0, y0, z0 as your point. So the equation of the tangent plane is going to be 12 times x minus 2 minus 12 times y minus 2 plus 1 times z minus 3 equals 0. And again, what I did is I used the a, b, and c from the gradient vector as the coefficients, And I use the points here as your x sub 0, y sub 0, and z sub 0. Now you can go ahead and distribute and combine like terms to simplify that. I'm going to move on to find the parametric equations for the normal line. Again, to find the normal line, you need a point and you need that parallel vector. We're going to use the same point and the same parallel vector to find the equation of the tangent plane. I'm sorry, the symmetric equations, parametric equations for the normal line. So that is going to be the normal line is going to be in the form of x equals, so it's going to be x equals our starting x of 2 plus the first component of the normal vector, 2 plus 12t. Y is going to equal 2 minus 12t, and then z is going to equal 3 plus 1t. So those would be your parametric equations for the normal line at the point given.